Aerodynamics is the study of the behavior of air as it interacts with solid objects, such as an airplane wing, a car, or even a building. It is a branch of fluid dynamics and involves the analysis of the forces and the resulting motion of objects through the air. Here are the key points developed in detail. 1. Basic principles of aerodynamics. A. Airflow and streamlines. Airflow refers to the movement of air around an object. When an object moves through the air, it disturbs the air particles, creating a flow pattern. Streamlines are imaginary lines that represent the path of air particles as they flow around an object. They help visualize how air moves and interacts with surfaces. B. Forces in aerodynamics. There are 4 primary forces acting on an object in flight. Lift, the force that acts perpendicular to the direction of motion, allowing an object to rise. It is generated by the pressure difference between the upper and lower surfaces of an object, such as an airplane wing. Weight, the force due to gravity pulling the object downward. Thrust, the force that propels the object forward, typically generated by engines or propellers. Drag, the resistance force that acts opposite to the direction of motion, caused by friction and pressure differences. 2. Bernoulli's principle and lift. Bernoulli's principle states that an increase in the speed of a fluid, air, in this case, occurs simultaneously with a decrease in pressure. This principle is crucial in understanding how lift is generated. Airfoil shape. An airplane wing is designed with a curved upper surface and a flatter lower surface. As air flows over the wing, it travels faster over the curved top, creating lower pressure compared to the higher pressure on the bottom. This pressure difference generates lift. 3. Types of drag. Drag is a critical factor in aerodynamics, and it comes in several forms. Parasite drag, caused by the shape and surface roughness of the object. It includes form drag, due to the shape, and skin friction drag, due to the surface texture. Induced drag, generated by the creation of lift. It is a byproduct of the wing generating lift and is influenced by the wing's aspect ratio, the ratio of its length to its width. For applications of aerodynamics. Aerodynamics plays a vital role in various fields: aviation, designing aircraft to optimize lift, reduce drag, and improve fuel efficiency. Automotive, shaping cars to reduce drag, improve fuel efficiency, and enhance stability at high speeds. Sports, designing equipment like bicycles, helmets, and golf balls to minimize air resistance and improve performance. Architecture, designing buildings to withstand wind forces and reduce wind-induced vibrations. 5. Computational fluid dynamics, CFD. Modern aerodynamics heavily relies on computational fluid dynamics, CFD. CFD uses numerical methods and algorithms to solve and analyze problems involving fluid flows. It allows engineers to simulate airflow around objects, predict aerodynamic performance, and optimize designs without extensive physical testing. 6. Wind tunnels. Wind tunnels are essential tools in aerodynamics research. Wind tunnel testing involves placing scale models of objects in a controlled airflow environment to study their aerodynamic properties. This helps validate CFD simulations and refine designs. Practical example: airplane wing design. Consider the design of an airplane wing shape. The wing is designed with a specific airfoil shape to maximize lift and minimize drag. Angle of attack, the angle between the wing's chord line, a straight line from the leading to the trailing edge, and the oncoming airflow. Adjusting this angle affects lift and drag. Winglets, small vertical extensions at the wingtips that reduce induced drag by controlling the airflow around the wingtip vortices. Conclusion: aerodynamics is a complex and fascinating field that combines principles of physics, engineering, and mathematics to understand and optimize the interaction between air and solid objects. Its applications are vast, impacting industries from aviation to automotive to sports and beyond. Bernoulli's principle is a fundamental concept in fluid dynamics, named after the Swiss mathematician and physicist Daniel Bernoulli. It describes the behavior of a fluid, liquid or gas, moving along a streamline. Let's break it down in detail. Bernoulli's principle explained. 1. The principle itself. Bernoulli's principle states that in a steady flow, the sum of the pressure energy, kinetic energy, and potential energy per unit volume of a fluid remains constant. Mathematically, it can be expressed as P plus 21 V2 plus GH equals constant, where P is the static pressure, \rho is the fluid density, V is the fluid velocity, G is the acceleration due to gravity, H is the height above a reference point. 2. Conservation of energy. Bernoulli's principle is derived from the conservation of energy. It implies that an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. This can be understood as follows: kinetic energy \frac 1 2 \rho v caret 2. Potential energy \rho gh. Pressure energy P. In a flowing fluid, if the velocity increases, the kinetic energy increases. To maintain the energy balance, either the pressure must decrease or the height must decrease, or both. 3. Applications of Bernoulli's principle. A. Airplane wings lift generation. The shape of an airplane wing, airfoil, is designed so that air flows faster over the top surface than the bottom surface. According to Bernoulli's principle, the faster airflow over the top creates lower pressure compared to the higher pressure on the bottom, generating lift. B. Venturi effect flow measurement. In a Venturi tube, the fluid speed increases as it passes through a narrow section, causing a drop in pressure. This principle is used in devices like carburetors and flow meters to measure the flow rate of fluids. C. Atomizers spray mechanisms. In devices like perfume sprayers and carburetors, a high-speed jet of air creates a low-pressure area that draws liquid up through a tube, atomizing it into a fine mist. For real-world examples, A. Chimney smoke extraction. Wind blowing across the top of a chimney creates a low-pressure area, helping to draw smoke up and out of the chimney. B. Sailing sailboats. The curved shape of a sail acts like an airfoil. Wind flowing faster over the curved side of the sail creates lower pressure, generating a force that propels the boat forward. Bernoulli's principle is a cornerstone of fluid dynamics, explaining how changes in velocity, pressure, and height interact in a moving fluid. Its applications are vast, from aviation to everyday devices like spray bottles and chimneys. The Venturi effect is a fascinating phenomenon in fluid dynamics, named after the Italian physicist Giovanni Battista Venturi. It describes how the pressure of a fluid decreases as the fluid flows through a constricted section of a pipe. Let's explore this in detail. Venturi effect explained. 1. Basic concept. The Venturi effect occurs when a fluid flows through a pipe that narrows at some point. As the fluid enters the narrower section, its velocity increases, and its pressure decreases. This relationship is a direct consequence of the principles of conservation of mass and energy. 2. Mathematical description. The Venturi effect can be described using Bernoulli's equation and the continuity equation. Continuity equation. This principle states that the mass flow rate must remain constant from one cross-section of a pipe to another. For an incompressible fluid, this can be written as a 1v1 equals a 2v2, where a is the cross-sectional area and v is the fluid velocity. Bernoulli's equation. For an incompressible, non-viscous fluid, Bernoulli's equation along a streamline is P plus 2 1v2 plus GH equals constant, where P is the pressure, \rho is the fluid density, V is the velocity, and H is the height above a reference point. Combining these principles, we can understand that as the fluid velocity increases in the narrower section, the pressure must decrease to conserve energy. 3. Applications of the Venturi effect. 8. Flow measurement. Venturi meters. These devices measure the flow rate of a fluid by constricting the flow and measuring the pressure difference between the wider and narrower sections. The flow rate can be calculated using the pressure difference and the known cross-sectional areas. B. Fluid mixing. Carburetors. In internal combustion engines, carburetors use the Venturi effect to mix air and fuel. The reduced pressure in the narrow section draws fuel into the airflow, creating a combustible mixture. C. Medical devices. Venturi masks. These masks deliver a precise concentration of oxygen to patients. The Venturi effect ensures that a specific amount of air is mixed with the oxygen, allowing for controlled oxygen delivery. D. Industrial applications. Vacuum pumps. Some vacuum pumps use the Venturi effect to create a vacuum by accelerating a fluid through a narrow section, reducing the pressure and drawing in surrounding air or fluid. Real-world example, Venturi tube. A Venturi tube is a practical application of the Venturi effect. It consists of a tube with a narrow throat in the middle. As fluid flows through the tube, its velocity increases at the throat, causing a drop in pressure. This pressure difference can be measured to determine the flow rate. The Venturi effect is a powerful principle in fluid dynamics with numerous practical applications. By understanding how fluid velocity and pressure interact in constricted spaces, engineers and scientists can design efficient systems for measuring flow, mixing fluids, and creating vacuums. The Venturi effect plays a significant role in aircraft design, particularly in understanding and optimizing airflow around various components of the aircraft. Here's a detailed look at how it impacts aircraft design. 1. Airfoil design and lift generation. The Venturi effect helps explain how lift is generated on an airplane wing. Airfoil shape. The wing's airfoil shape is designed so that air flows faster over the curved upper surface than the flatter lower surface. This increase in velocity over the top surface leads to a decrease in pressure, according to the Venturi effect and Bernoulli's principle. The higher pressure on the bottom surface compared to the lower pressure on the top surface creates lift, which is essential for flight. 1. 2. Engine inlets and efficiency. Aircraft engines, particularly jet engines, utilize the Venturi effect to optimize airflow. Inlet design. The shape of the engine inlets is designed to accelerate the airflow as it enters the engine. This acceleration reduces the pressure, allowing for more efficient compression and combustion within the engine. This design helps improve the overall efficiency and performance of the engine. 3. Pitot tubes and airspeed measurement. The Venturi effect is also used in instruments that measure airspeed, pitot tubes. These devices measure the dynamic pressure of the airflow. As air enters the narrow opening of the pitot tube, its velocity increases, causing a drop in pressure. This pressure difference is used to calculate the airspeed of the aircraft, which is crucial for safe and efficient flight operations. 4. Cabin ventilation systems. Aircraft cabin ventilation systems leverage the Venturi effect to ensure proper airflow. Ventilation ducts. The design of ventilation ducts often includes constricted sections to accelerate airflow and reduce pressure. This helps in efficiently distributing air throughout the cabin, maintaining a comfortable environment for passengers and crew. 5. Aerodynamic optimization. Overall aerodynamic optimization of the aircraft benefits from understanding the Venturi effect. Flow control devices. Devices such as vortex generators and winglets are designed to manage airflow around the aircraft. By controlling the velocity and pressure of the airflow, these devices help reduce drag and improve lift, enhancing the aircraft's performance and fuel efficiency. The Venturi effect is integral to various aspects of aircraft design, from generating lift to optimizing engine performance and ensuring efficient cabin ventilation. By understanding and applying this principle, aerospace engineers can design more efficient, safer, and higher-performing aircraft. Designing efficient cabin ventilation for large aircraft involves addressing several complex challenges to ensure passenger comfort, safety, and energy efficiency. Here are some of the key challenges. 1. Thermal comfort and air quality. 8. Temperature control. Uniform temperature distribution. Ensuring a consistent temperature throughout the cabin is difficult due to varying heat loads from passengers, electronic devices, and external environmental conditions. 1. Localized comfort. Different passengers have different comfort preferences, making it challenging to maintain an optimal temperature for everyone. 2. B. Air quality. Contaminant control. Efficiently removing contaminants such as pathogens, volatile organic compounds, VOCs, and other pollutants is crucial for maintaining air quality. 3. Humidity levels. Maintaining appropriate humidity levels is essential to prevent discomfort and health issues, but it is challenging due to the dry air at high altitudes. 3. 2. Energy efficiency. 8. Power consumption. Energy use. Ventilation systems consume significant amounts of energy. Designing systems that provide adequate ventilation while minimizing energy consumption is a major challenge. 1. Heat removal efficiency. Efficiently removing heat generated by passengers and electronic devices without excessive energy use is critical. 2. 3. System complexity and weight. A. Duct design. Complex ductwork. Designing and installing complex duct systems that distribute air evenly throughout the cabin without adding excessive weight is challenging. 1. Space constraints. The limited space within the aircraft structure makes it difficult to design and integrate ventilation systems. 4. Noise control. 8. Minimizing noise. Quiet operation. Ensuring that ventilation systems operate quietly to avoid disturbing passengers is essential. This requires careful design of fans, ducts, and air outlets. 2. 5. Safety considerations. 8. Fire and smoke control. Fire safety. Ventilation systems must be designed to prevent the spread of smoke and fire within the cabin, which adds complexity to the design. 3. Emergency ventilation. Ensuring that the system can provide adequate ventilation in emergency situations, such as decompression or smoke events, is critical. 3. 6. Innovative ventilation concepts. A. Advanced ventilation techniques. Microjet ventilation. New concepts like ceiling-based microjet ventilation systems are being explored to improve air distribution and energy efficiency. 1. Displacement ventilation. This technique involves supplying air at low velocities near the floor and extracting it near the ceiling, which can improve thermal comfort and air quality. 1. Designing efficient cabin ventilation for large aircraft requires balancing multiple factors, including thermal comfort, air quality, energy efficiency, system complexity, noise control, and safety. Innovations in ventilation technology and careful design considerations are essential to meet these challenges and ensure a comfortable and safe environment for passengers. Aircraft ventilation systems are designed with multiple layers of safety to handle smoke in emergencies. Here are the key aspects of how these systems manage smoke. 1. Smoke detection. 8. Smoke detectors. Placement: smoke detectors are strategically placed throughout the aircraft, including in the cabin, cargo holds, lavatories, and avionics bays. 1. Types: these detectors can be optical, detecting smoke particles, or ionization-based, detecting changes in air ionization due to smoke. 2. Smoke evacuation. Aid ventilation system activation. Emergency ventilation: when smoke is detected, the aircraft's ventilation system can be configured to increase the airflow to evacuate smoke from the cabin and cockpit. 1. Airflow management: the system directs fresh air into the cabin while expelling smoke-laden air through designated exhaust vents. 2. 3. Isolation and containment. 8. Compartmentalization. Fire-resistant barriers: aircraft are designed with fire-resistant barriers to contain smoke and prevent it from spreading to other parts of the aircraft. 2. Sealed compartments: cargo holds and other critical areas are sealed to contain smoke and fire, minimizing the risk to passengers and crew. 3. 4. Crew procedures. 8. Emergency protocols. Checklists: pilots and cabin crew follow specific checklists and procedures to manage smoke events. These include donning protective breathing equipment and isolating affected areas. 3. Communication: clear communication between the cockpit and cabin crew ensures coordinated efforts to manage the situation and keep passengers informed. 3. 5. Protective equipment. 8. Breathing apparatus. Protective breathing equipment: PBE crew members are equipped with PBEs that provide clean air and protect against smoke inhalation. 1. Passenger oxygen masks. In severe smoke situations, passenger oxygen masks can be deployed to provide clean air directly to passengers. 2. 6. Regulatory standards. 8. Compliance with regulations. FAA and EASA standards. Aircraft ventilation and smoke management systems must comply with stringent regulations set by aviation authorities like the FAA, Federal Aviation Administration, and EASA, European Union Aviation Safety Agency. 1. Testing and certification. These systems undergo rigorous testing and certification to ensure they can effectively manage smoke in emergency situations. 1. Aircraft ventilation systems are meticulously designed to detect, contain, and evacuate smoke in emergencies. Through a combination of advanced detection technologies, strategic airflow management, compartmentalization, and strict regulatory compliance, these systems ensure the safety and well-being of passengers and crew during smoke events. Aircraft ventilation systems are designed with multiple safety features to handle fire emergencies effectively. Here's a detailed look at how these systems manage fire situations. 1. Fire detection. Sensors and alarms. Smoke and fire detectors: these are strategically placed throughout the aircraft, including in the cabin, cargo holds, and avionics bays. They detect the presence of smoke or fire and trigger alarms. 1. Warning systems. Once a fire is detected, the system alerts the crew through visual and auditory alarms, enabling them to take immediate action. 2. Fire suppression. 8. Built-in fire suppression systems. Extinguishing agents. Aircraft are equipped with fire suppression systems that use agents like halon to extinguish fires. These systems can be activated manually by the crew or automatically upon detection of a fire. 3. Engine and APU fire suppression. Specific systems are in place to handle fires in the engine and auxiliary power unit (APU) areas. These include firewalls and extinguishing systems that isolate and suppress the fire. 4. 3. Ventilation and smoke evacuation. 8. Airflow management. Emergency ventilation. The ventilation system can be adjusted to increase airflow, helping to evacuate smoke from the cabin and cockpit. This involves directing fresh air into the cabin while expelling smoke-laden air through designated exhaust vents. 5. Additional outflow valves. Some aircraft are equipped with additional outflow valves that can be opened to enhance smoke evacuation during a fire. 6. 4. Isolation and containment. 8. Compartmentalization. Fire-resistant barriers. Aircraft are designed with fire-resistant barriers to contain fires and prevent them from spreading to other parts of the aircraft. 7. Sealed compartments. Critical areas like cargo holds are sealed to contain smoke and fire, minimizing the risk to passengers and crew. 8. 5. Crew procedures. 8. Emergency protocols. Checklists. Pilots and cabin crew follow specific checklists and procedures to manage fire emergencies. These include donning protective breathing equipment and isolating affected areas. 9. Communication. Clear communication between the cockpit and cabin crew ensures coordinated efforts to manage the situation and keep passengers informed. 9. 6. Protective equipment. 8. Breathing apparatus. Protective breathing equipment. PBE crew members are equipped with PBEs that provide clean air and protect against smoke inhalation. 10. Passenger oxygen masks. In severe smoke situations, passenger oxygen masks can be deployed to provide clean air directly to passengers. 10. Conclusion. Aircraft ventilation systems are meticulously designed to detect, contain, and suppress fires while ensuring the safety of passengers and crew. Through advanced detection technologies, strategic airflow management, compartmentalization, and strict regulatory compliance, these systems effectively manage fire emergencies. Managing fire suppression on supersonic aircraft presents unique challenges due to the extreme conditions and advanced technologies involved. Here are some of the key challenges. 1. High-speed aerodynamics. Extreme temperatures. Heat generation. Supersonic speeds generate significant aerodynamic heating, with skin temperatures reaching up to 212 degrees Fahrenheit, 100 degrees Celsius, at Mach 2.01. This can affect the performance and reliability of fire suppression systems. Material constraints. Materials used in fire suppression systems must withstand these high temperatures without degrading or losing effectiveness. 1. 2. Rapid response requirements. Speed of fire spread. Quick suppression needed. Fires can spread rapidly in the high-speed airflow conditions of supersonic flight, necessitating extremely fast detection and suppression mechanisms. 2. Automated systems. Manual intervention may not be feasible, so automated fire detection and suppression systems are critical. 2. 3. Weight and space limitations. Compact design. Space constraints. Supersonic aircraft designs prioritize aerodynamics and weight reduction, leaving limited space for fire suppression systems. 2. Lightweight materials. Fire suppression systems must be lightweight to avoid negatively impacting the aircraft's performance and fuel efficiency. 2. 4. Environmental considerations. Emissions and regulations. Environmental impact. Fire suppression agents must be effective without contributing to environmental harm, such as ozone depletion or toxic emissions. 3. Regulatory compliance. Systems must comply with stringent environmental regulations, which can limit the types of suppression agents that can be used. 3. 5. System reliability. High reliability standards. Redundancy. Fire suppression systems must have redundant components to ensure reliability in the event of a failure. 2. Maintenance. Regular maintenance and testing are essential to ensure the systems function correctly under the extreme conditions of supersonic flight. 2. 6. Integration with other systems. 8. Compatibility. System integration. Fire suppression systems must be seamlessly integrated with other aircraft systems, such as avionics and environmental control systems, to ensure coordinated responses during emergencies. 2. The challenges of managing fire suppression on supersonic aircraft are multifaceted, involving high-speed aerodynamics, rapid response requirements, weight and space limitations, environmental considerations, system reliability, and integration with other systems. Addressing these challenges requires advanced materials, innovative design solutions, and rigorous testing to ensure the safety and effectiveness of fire suppression systems in the demanding environment of supersonic flight. The aerodynamics, as a scientific discipline, has a rich history that spans centuries, evolving from early observations and theories to the sophisticated field it is today. Let's explore how aerodynamics emerged and developed over time. 1. Ancient observations and early theories. Early concepts. Aristotle and Archimedes. In ancient Greece, philosophers like Aristotle and Archimedes laid the groundwork for fluid dynamics. Aristotle's work on the continuity of fluids and Archimedes' principle of buoyancy were early contributions to understanding fluid behavior. 1. Mythology and early flight attempts. Icarus and Daedalus. The Greek myth of Icarus and Daedalus reflects humanity's early fascination with flight. Although mythical, these stories inspired future generations to explore the possibility of human flight. 2. Renaissance and the birth of modern science. Leonardo da Vinci. Flying machines. Leonardo da Vinci's sketches and studies of flying machines in the late 15th century were among the first systematic attempts to understand and replicate bird flight. His designs, though not practical, demonstrated an early understanding of aerodynamics. 1. 17th and 18th centuries, foundations of aerodynamics. Isaac Newton. Theory of air resistance. In 1726, Isaac Newton developed a theory of air resistance, proposing that the resistance experienced by an object moving through air is proportional to the square of its velocity. This was a significant step towards understanding aerodynamic drag. 3. Daniel Bernoulli. Bernoulli's principle. In 1738, Daniel Bernoulli published Hydrodynamica, where he described the relationship between pressure, velocity, and density in a fluid. Bernoulli's principle became fundamental in explaining how lift is generated on an airfoil. 1. 19th century, advancements and practical applications. George Cayley. For forces of flight, George Cayley, often called the father of aerodynamics, identified the four fundamental forces of flight: lift, thrust, drag, and weight. In 1799, he developed the concept of the modern fixed-wing aircraft, laying the foundation for future aviation. 1b. Wind tunnels. First wind tunnel. The construction of the first wind tunnel in 1871 allowed for controlled experiments on airflow and aerodynamic forces. This was crucial for validating theories and improving aircraft designs. 5. Early 20th century, the age of flight. 8. Wright brothers. First powered flight. On the 17th of December 1903, Wilbur and Orville Wright achieved the first successful powered flight. Their meticulous experiments with gliders, wind tunnels, and propellers were grounded in aerodynamic principles, marking a significant milestone in aviation history. 1b. Ludwig Prandtl. Boundary layer theory. Ludwig Prandtl's work on boundary layers in the early 20th century provided a deeper understanding of how air flows over surfaces, leading to more efficient aircraft designs. 6. Mid to late 20th century, the jet age and beyond. 8. Supersonic and hypersonic flight. Compressible flow. Advances in understanding compressible flow, turbulence, and shock waves enabled the development of supersonic and hypersonic aircraft. Theoretical and experimental work in this area expanded the boundaries of aerodynamics. 1b. Computational fluid dynamics, CFD. Numerical simulations. The advent of computers allowed for the development of CFD, which uses numerical methods to simulate airflow around complex shapes. This has become an essential tool in modern aerodynamics, enabling detailed analysis and optimization of aircraft designs. 1. Conclusion. Aerodynamics emerged from early observations and theories about fluid behavior, evolving through centuries of scientific inquiry and technological advancements. From the foundational work of ancient philosophers to the pioneering efforts of modern scientists and engineers, aerodynamics has become a critical field that underpins the design and performance of aircraft and many other technologies. That was all. Goodbye.